Welcome to the Deep Dive, the only place where we take a stack of dense, fascinating source material and distill it into pure, actionable knowledge designed just for you. Today, we are undertaking a serious deep dive into material extrusion, or MEX.
Which for most people, that's really just the technical term for the most common kind of 3D printing you see, right? The one that sort of squirts out melted material layer by layer.
Exactly. But we are moving way beyond the basic hobbyist printer sitting on a workbench. Your sources reveal that MEX it's no longer just a toy or a prototyping tool. It's rapidly evolved into this sophisticated industrial process.
And everything from personalized medicine and high-performance engineering to, large-scale construction.
So our mission today is to cut through the mechanics, understand the just astonishing variety of materials that are now being used, and connect all those technical details to the surprising places they're showing up.
We want you to walk away understanding not just what MX is, but really why it matters right now.
Okay, let's start at the very beginning, the fundamental definition. If someone asks what material extrusion is, how do we sum it up simply?
Well, it's an additive manufacturing process where material, and that can be anything, from a solid filament to a thick paste or even a liquid slurry, is pushed or dispensed through a controlled opening.
Like a nozzle.
Exactly, like a nozzle or an orifice. The key is that control. You're forming these precise two-dimensional cross-sections, and by stacking them again and again, you build the final three-dimensional object from the ground up.
It sounds deceptively simple, almost like drawing with a controlled glue gun. But that simplicity is where its power lies, isn't it?
Absolutely. That foundational simplicity combined with low operating costs and the ability to create geometries that are just impossible with traditional manufacturing. That's why MEX totally dominates the 3D printing market today.
Okay, let's unpack this. Where did this stack of layers begin? When people talk about this, they usually say fused filament fabrication, FFF, which is the modern open source term for what was originally patented as fused deposition modeling, or FDM.
That's right. The core idea of FFF is very straightforward. You take a solid plastic wire, the filament, and you feed it into a highly precise heating element.
The hot end.
The hot end, where it melts. And then a mechanism forces that molten material through a nozzle onto the build platform.
And the origin story here is a great little anecdote. It started with Scott Crump back in 1988, trying to solve a pretty common problem.
Right. He was just trying to create a custom toy for his daughter, experimenting by extruding hot plastic mixture through a syringe.
A kitchen counter experiment that literally launched an entire industry.
It did.
Yeah.
Crump patented the FDM technology, co-founded Stratasys, and by '92 they had their first commercial machine out, the 3D modeler. For decades, FDM was the tightly controlled gold standard for industrial rapid prototyping.
But the technology truly exploded when it left that proprietary sphere. So if Crump had the patent, what was the inflection point that made this so accessible?
It was the calendar. When the core FDM patent expired around 2005, it was effectively just unleashed. This sparked the now famous open-source RepRap project, the Replicating Rapid Prototyper, which aimed to create a 3D printer that could print most of its own parts.
Self-replicating machine. That's a wild idea.
It was revolutionary. I mean, this open source shift popularized the term FFF. It lowered the barrier to entry so much, and it led to this massive influx of hobbyist and small business butchers we see today.
That's what took it from a niche industrial thing to a household name.
For sure. It stimulated massive competition and innovation. It's fascinating how the sunset of a single IP protection can just fundamentally restructure an entire global industry.
And as it matured, engineers realized they could extrude a lot more than just standard plastic filament.
And that realization leads us right into the mechanical variety we have today.
Right. The sources make it clear that while FFF is kind of the face of MEX, there are three fundamentally distinct ways to push material out, depending on what state it's in.
Precisely. We have three primary extruder mechanisms, each one optimized for a different kind of raw material.
And we know the classic one, filament-based extrusion.
Right, the standard FDM FFF setup. It uses rollers, often geared, to precisely feed that solid wire,
the filament,
into a heated chamber. Its advantage is super high precision, great for continuous printing with thermoplastics. The limitation, of course, is that you have to process your material into that exact wire format first.
Which adds cost and complexity. So that's great for prototyping, but if you want high volume, high speed, or just to use cheaper raw inputs, you need something else.
Which brings us to screw extrusion. This is used in methods like fused granular fabrication, or FGS.
Right, or pellet material extrusion.
Exactly. Here, instead of a filament spool, you load raw granules, pellets, even recycled powders directly into a hopper. A large internal rotating screw and auger advances, compresses, and melts the material, forcing it out.
So you completely bypass the energy and cost of turning the raw material into that precise wire form first.
You do. This is ideal for rapid, high-volume production. It drastically lowers material costs because you're using industrial-grade, bulk, raw polymers. The trade-off is the equipment is usually bigger, more expensive, and often has slightly lower resolution.
And the third one handles materials that are neither solid plastic nor raw granules, the tricky stuff, like gels or pastes.
That is plunger extrusion. In this case, no moving screws, no rollers. The material, a highly viscous paste or slurry, is held in a pressurized chamber, and a piston or plunger just pushes it out with controlled force.
And that's for what? Really dense materials?
Perfect for things like structural ceramics, cement, high-concentration hydrogels, or even soft materials like specialized food pastes.
So what's the major mechanical difference here, the advantage?
The advantage is providing extremely high, precise pressure. The major limitation, though, is that it's an intermittent process. You're limited by the volume of that chamber, so you have to stop and reload the reservoir. It's not continuous like screw or filament feeds.
And this plunger approach is often categorized under the umbrella of direct ink writing, isn't it?
It is. Direct ink writing, or DIW, is all about using these semi-liquid or highly viscous paste feedstocks. And they often rely on chemical reactions, not just heat, to solidify.
So, like curing with UV light or something.
Exactly. Some DIW inks cure instantly with UV light, or they cross-link chemically, making them way more versatile than simple plastics that just set when they cool.
That totally challenges the initial idea that 3D printing is just plastic melted by heat. We're dealing with a huge material spectrum here.
It's vast. We can start with the staples, the thermoplastics.
Right, you've got your PLA, polylactic acid. It's the darling of desktop printing because it's so easy to work with, minimal shrinkage, and it's biodegradable.
But the flip side is it's poor temperature resistance, and it's pretty brittle. You don't want to use PLA for something that's going to carry a load or sit out in the sun.
So then you step up to ABS, acrylonitrile butadiene styrene.
The engineering workhorse. High impact strength, great chemical resistance. But ABS introduces that notorious printing challenge. High thermal shrinkage.
That's the warping.
That's the warping. It can shrink up to 0.8%, which causes the part to curl right up off the bed. To manage that, you almost always need a heated bed and a fully enclosed heated chamber.
And I was surprised to see how fast material science is moving. If we want something structurally sound, we quickly get beyond base polymers and into composites. How are engineers using MEX to make plastic perform like metal?
By embedding reinforcement. The simplest way is mixing short carbon or glass fibers into the polymer matrix, like a high-performance nylon. That significantly boosts stiffness and mechanical strength.
But the crucial insight, the real paradigm shift, is the technique that allows for structural substitution.
That's when you embed continuous fibers. So instead of short random bits of carbon fiber, you're printing a layer of polymer and at the same time laying down an unbroken thread of carbon or glass fiber.
So it's like creating rebar inside the plastic.
It's exactly like rebar. It often requires these complex multi-headed systems, but the result is transformative. You get a 3D printed part that can structurally rival aluminum in certain directions. That is the future.
And speaking of materials that act nothing like plastic, we have those slurries and pastes for construction and biomedicine. You need a material that can basically defy gravity the second it lands.
Exactly. When you're printing thick walls of concrete or delicate tissue scaffolds, the material must flow like a liquid under pressure, but instantly set and hold its shape the moment that pressure is released.
Otherwise, the whole thing just collapses.
It collapses under its own weight. This is a crucial physical requirement.
And the technical term for that behavior is what?
It's called high shear thinning viscosity. It means the viscosity, the thickness, changes dramatically based on the mechanical stress, or shear, you apply to it. This rheological control is what lets us build upward with concrete or hydrogels.
Okay, moving on to the physics of precision. How do engineers actually fine-tune this process to get quality parts?
The control parameters are meticulous. Take the nozzle. The diameter is a fundamental trade-off. A small nozzle, say 0.1 millimeters, gives you incredible detail, but it slows the print to a crawl.
And a big nozzle gives you speed but no detail.
Right. A 1 millimeter nozzle is fast, great for massive objects, but you sacrifice all fine precision.
And the internal structure, the infill, that's not just filler, it's a structural choice.
Absolutely. Infill, you can dial it from a lightweight 10% up to a fully solid 100%. It determines strength, weight, print time. And engineers pick specific patterns, hexagonal, rectilinear, to align with the stress loads of the final part.
But none of that matters if the layers don't stick together. That's the most crucial part, right? The physics of fusion.
This is where we talk about layer bonding. It's not just stacking wet materials, it's fusing them. The best analogy I've heard is trying to stick two cold ice cubes together. They just sit there.
Right.
But if you slightly melt the surface of both cubes, they freeze together, and suddenly you can't tell where one started and the other ended.
That's a perfect analogy. The heat is the catalyst.
There's thermal diffusion. The new hot layer of polymer has to partially remelt the surface of the previous cooler layer. This softening lets the individual polymer chains, the molecules themselves, to sort of wiggle across that boundary.
And that intermingling, that's the bond.
That intermingling is chemical diffusion, and that is what guarantees a true, strong adhesion. If your temperature or cooling rate is off, you just don't get enough diffusion.
And when diffusion fails, we end up with one of the biggest limitations of 3D printing, anisotropy.
Correct. Anisotropy means the material strength is different depending on the direction. Think of wood grain. It's incredibly strong lengthwise, but splits easily across the grain.
I see.
In a failed print, the part is strong on the horizontal plane, where the material is continuous but extremely weak vertically along those layer lines because the bonding was bad. Overcoming that is the holy grail of MX research.
And finally, even a perfectly printed part often needs one more step. Post-processing. It's the finish line to get to end-use quality.
It often is. Your sources highlight three main categories for this.
Okay, let's start with the chemical methods.
The main one is vapor smoothing, often using a solvent like acetone for ABS. The vapor partially dissolves the surface, which eliminates the visible layer lines. It dramatically improves the look and feel.
But you have to be careful not to melt your details away.
Exactly. It's a fine line. It can risk your dimensional accuracy.
Then there are thermal methods.
That's annealing. It's a controlled heating and cooling after the print is done. This is mainly to relieve internal stresses that built up during the rapid cooling of the print process.
So it makes the part stronger overall.
It improves the mechanical properties, yes. Though again, engineers have to balance that against the risk of the part shrinking or deforming during the heat cycle.
And finally, coatings, which can add all kinds of new functions.
You see everything. Simple lacquer or epoxy resin for durability, all the way up to highly specialized coatings. You can use metallization to make a plastic part corrosion resistant, or specialized antibacterial coatings with silver or zinc oxide for medical parts.
So what does this whole complex process mean in the real world? Where are we seeing the biggest impact?
The biggest impact is in fields where customization is everything, and medicine leads that charge. We're using MEX to rapidly manufacture personalized prostheses, patient-specific implants, sophisticated drug delivery systems.
Can you give us a specific material example there?
Certainly. Researchers are using plunger extrusion with complex slurries to print porous magnesium scaffolds for bone tissue engineering.
Magnesium? Why magnesium?
It's bioresorbable, meaning it supports the initial bone growth and then it just safely dissolves away in the body over time. It's tailoring the material to the patient's exact biological needs.
That's the ultimate tailor-made solution. Okay, shifting from the microscopic to the massive. Construction printing houses still sounds like science fiction.
But it's really happening today with large-scale MEX. You use high-volume screw or plunger extruders to handle these viscous cement and concrete mixes. The benefit is twofold. You get geometric freedom for architects to design these amazing curved shapes, and you get incredible speed.
How fast are we talking?
Sources report that the walls for an entire house can be printed in as little as 24 hours to a few weeks. It just drastically cuts down on construction time, minimizes waste, and lowers labor costs.
That is game-changing efficiency.
We're seeing major projects, globally printed offices, bridges, entire housing developments.
And finally, what about specialty applications, like food?
Right, food printing. This uses highly controlled plunger or screw extruders for soft materials like chocolate, dough, or vegetable purees. It's used for culinary art, sure, but the functional application is huge. It's being used to create textured food for patients with dysphagia swallowing difficulties, to make sure they get nutrition in a form they can safely consume.
Wow. We've covered a massive amount of ground today. From Scott Crump's kitchen experiment to the 3 different extruder types, the material science of continuous fibers, the rheology of these pastes, all the way to customized medicine and printed houses.
Material extrusion is versatile, it's economical, and it's still the most dynamically developing additive manufacturing technology out there.
What stands out to me is how the biggest limitations, that dimensional accuracy and that pesky layer anisotropy, are actually what's driving the core innovation.
Absolutely. Those issues, the struggle to get every layer chemically bonded and the need for post-processing to hide the lines, those are still the main challenges. But they are being steadily overcome.
The ultimate goal is a part that's perfectly homogeneous, printed in seconds, with zero post-processing.
Which raises an important question for you to think about. Our discussion highlighted this critical challenge of achieving perfect thermal and chemical diffusion between layers. So, if future MEX technology can reliably achieve perfect, homogeneous chemical bonding between every single layer, eliminating anisotropy, making a printed part functionally identical to a molded one, how will that fundamental change in material consistency affect our future mechanical testing standards? When a part can be customized with microscopic precision, will traditional material property standards even apply anymore?
That is a profound thought. If the material is truly perfect in all directions, the whole world of engineering changes. Thank you for joining us on the Deep Dive.